from the homework I assigned yesterday. Number 7 on the spring page. Okay, here we go. So, Canwell wants to know about number 7. Yeah, you good? Your list of... You're looking at your signatures, your meaningless signatures? Okay. So, some joke glasses with eyeballs on springs have springs with an equilibrium length of 10 centimeters and a constant of 25 newtons per meter. A party goer is wearing the joke glasses and the springs are extended forward to a length of 26 centimeters. He jerks his head backward and the springs reduce in length to 1.2 centimeters. By how much is the energy stored in the springs reduced? Okay, so.
Can I take a guess?
Would you like to guess?
Well, I'm working through the question to see.
Let's do it. How do you want to do it, Connor?
Alright, so we know the equilibrium of the spring, so where it's like neutral point is 10 centimeters. So if they say the glass or the spring thingy moves out 26, it's only actually moving 16 then because.
No, it says to a length. Yes, it says to a length of 26. Yeah.
So it would only. But the difference is 16. Is
Yeah.
the point?
Yeah.
So that's the number we really need to know.
Yeah.
And then back again to 1.2. I can't honestly remember what I wrote here. Let's see. The question is 7. I wrote something.
It's good that you wrote something.
I think that's it. No, that's not right. 0.148, I guess.
So, Ken, you see what's going on here, though? So we've got a 10 centimeter spring. It gets extended to 26 centimeters, which means this has an extension of 16 centimeters. Then it gets reduced to 1.2, which is a contraction of 8.8. So what you're going to want to do is you're going to want to find what the potential energy is here using half kx squared. You're going to find the potential energy here, half kx squared, and you're going to, how much is this energy stored in the springs reduced? PE final minus PE initial is what you're going to want to do. Any other questions from anything I assigned? Good, Kirat. Also in this one? Right, because there's only, this is number 6 right here. So let's explain to you what I tried to explain to Naya and was it Jasmine who came in at lunch? So on number 6, you've got a spring with a force constant of 500 newtons per meter is extended from its equilibrium length by 12 centimeters. So here was at the equilibrium length. It gets extended by 12. From the extended length, it's shortened by 7 centimeters. So now it has a new extension of 5. And then from that, it's shortened by 15, which brings us back 5 to the equilibrium, and then a compression of 10. The question wants to know how much does the spring's elastic potential change during the first time it's shortened. So what I recommended be done is that the potential energy be found at each state, like the 12 centimeter extended, the 5 centimeter extended, and the 10 centimeter compression in each one of those. And then the change in potential energy is going to be final minus initial. So it's going to be this minus this, because this is the extension change to this. And then it's going to be this minus this. And those will be the two values for the change in elastic potential energy. Is that enough? Okay. Anybody else? Anything I assigned from homework yesterday? We're cool with the power stuff? Yeah, now. For these ones? No. I do not have values. We could calculate them relatively easily at this point, but no, I do not have values. Do you have values you want to check? Because we could just do physics by democracy. Okay, number 6. Who's got an answer for us for number 6? What'd you get, Connor? Did you do it the way I outlined it just now here? You know what? I could just calculate it myself as well. We can verify if Connor's correct. So you didn't do it, okay?
No, I did it. It's just it's not gonna be your answers.
Okay, so this is 36,000.
Yeah, see, mine's a decimal point.
Point five, yes, okay, 500 times 5 squared. So this is going to be 6,250. So final minus initial, the elastic potential energy has decreased, whatever that minus 36,000 is.
Wait, so
Negative 29,750
Mr. Guidot?
is what I got for number 6A, 29,750, which seems really big, but oh, yeah, it totally is, because it's centimeters.
Yeah, that's what I was saying.
That's why I screwed that up.
No, that's why. Okay.
0.5 times 500 times 0.12 squared. Come on, Dawidoff. That's going to be 3.6, which makes that going to be 0.625.
Oh, that's what I did wrong. Okay.
Yeah, so that's 0.625 minus 3.6. So it's negative 2.975 joules. You got it? Okay. So if that's what you got for this one, then I'm willing to bet your answer for the second one is correct too.
I got pretty close to it.
Anybody else? Anything I assigned?
Yeah, 17.
Going back now to power.
Yeah, my problem is I want to check an answer because the answer is not.
We want to check answers. We can do this. What is the mass of an object traveling at 20 meters per second with...
How'd you get 20? I got 2. How does 0? Yeah, but why?
Okay, so hold on. Just let's look at this for Connor.
Yes, please.
Half
Maybe all of you are wrong.
mv squared. We know this is 4,000 is going to equal 0.5 times the mass. 20 meters per second squared is 400, is it not? Yes?
Yes.
So 4,000 divided by 400 is 10. Divided by 0.5 is 20, which is right there.
Where did I? Okay, I see.
So all of those 20 kilogrammers were ultimately correct. Yeah. The 0.5 kilogram rubber ball is thrown into the air at a height of 20 meters above the ground. It's traveling at 115 meters per second. What is the ball's kinetic energy? So that's just going to be half times a half times 15 squared. 0.5 times 0.5 times 15 squared. So your answer to A should be 56.25 if I'm not mistaken. Which is right there. Part B, what is the gravitational potential energy relative to the ground? So the potential energy relative to the ground is going to be 0.5 times 9.8, that times 20. It's going to be 98, which is this guy right here. So the question C says, how much work was done by someone at level ground throwing the ball into the air? So what the work is equal to change in energy, right? At ground level, does the ball have any potential energy? No. At ground, before it's thrown, does it have any kinetic energy? No. So when we're looking at energy final is, change in energy is energy final minus energy initial. And this is actually where we're going to go, probably not, well, maybe today, depending on how quickly you guys finish this lab, but tomorrow for sure. It has no initial energy. Finally, though, at the end of the problem, the way it's worded, is it now has kinetic energy and it has potential energy. So work is going to equal the kinetic energy final plus the potential energy final, which are these two values here. So I'm willing to bet this guy right here is actually C, this 154.3 joules. Because we take the 98 joules of potential and the 56.3 joules of kinetic, and you add those together, and that's total energy. Does that make sense? Any other questions about anything I assigned? Do we have values for this? Like, did anyone get values for this? Or did we just not do the spring questions I assigned? You didn't do them because you had questions about them?
What did it?
You just needed to get to them? Sorry, Jasmine, what was that? You didn't?
Like, I tried to do that.
Well, so this, but I'll give you an opportunity to answer questions now. Like, I'll take up any of these ones you want me to take up. Let's keep going? Okay, let's do 8. When an umbrella is opened, most of the work required to open it is done by the person using the umbrella, but a spring is used to complete the opening process. In the umbrella, a compressed spring with a length of 9.5 centimeters extends to a length of 10 centimeters, which does 0.12 joules of work expanding the umbrella. What is the constant of the spring? So, we're told that when the spring is compressed, it's 9.5 centimeters long. When it's allowed to relax, it's 10 centimeters long. So that means this guy right here, that 0.5 centimeters, is the compression of the spring. Now, to do work, the spring is going to decompress, right? It means it goes from its compressed length to its regular length. That's what it means to decompress. So work is equal to change in energy, and the kind of energy it has to start is going to be potential energy because of the compression of the spring. So work is equal to potential energy, well, and then after it's stretched out, there's going to be no final energy, right? Because the potential energy has been allowed to turn into useful joules of work. Okay? So all we need to figure out is, what we need to recognize is that the work done by the spring to expand itself is equal to the amount of potential energy it had stored in it. Does that make sense? So then work is going to equal 1/2 kx squared, which means my 0.12 joules of work is going to equal 1/2. Do we know this? No, that's what we're looking for, is the spring constant. And the x, remember, if you remember back to springs, x is the expansion or compression. So that's 1/2 centimeter, which is 0.005. Because 0.5 would be 50 centimeters, 0.05 would be 5 centimeters, 0.005 is 1/2 centimeter. So then to figure out our value for k, it's going to be 0.12 times 2 divided by 0.005 squared, which is going to give us a massive value. I get a k value of 9,600 newtons per meter. You forgot a z, yeah, and when you square the 0, it actually moves the decimal place twice. Yeah. So that's going to be 8. Is the process starting to make sense here? The translation between work and energy? I'm not hearing a lot of responses. Some of us are nodding. Okay, cool. And then number 9 was just an application of. Yeah, there was. 9 is just looking at the graph stuff that I gave you yesterday. How much work is required to extend the spring by 0.6 meters? That's just this area right here. And then question number 10. Each of the coil springs of a car has a spring constant of 25,000 newtons per meter. How much is each spring compressed if it supports 1/4 of the car's 12,000 newton weight? So 1/4 of 12,000 is 3,000. And that's going to become the FG that one spring is holding. We want FG. Ooh, oh, and this one's not a work question. This is just an FG equals F spring question. So I could have taken 10 out, I guess, technically. So FG, so then it's just going to be it's going to be, what is it, 3,000 equals KX. And we know K, so we can find X. And that's it. So 10's actually easier, slightly. Does this help? So then your compression is going to be 3,000 divided by 25,000. 12 centimeters is the value I got here for X. So those are the answers to the spring question. Now this one is, yeah, it's just going to be the work is equal to 1/2 the base times the height. So it's going to be 1/2, the base is 0.6, and the height is 150. Whatever that value is going to be the answer to number 9. Shapansky's room? Yep. Does that help? Does that make sense? Okay. Jasmine, does that help? Okay. The power questions, we were good at the power questions? There was no issues with those? Okay. The power ones I think are arguably easier. Springs are just different. If the power ones were good, then what I want you to do, don't do what I just did, which was flipping back. I want you to flip forward to this, the Stairmaster Lab. And this is where you guys are going to figure out your horsepower. It's going to be good. So in groups of 3, we need to, do we know our masses? I don't have a scale.
Yeah, I do.
There's got to be a scale up in the biology room or something. Does Mr. Clark have a scale? Like to weigh a human being?
Yeah, well,
Could you? Yeah, if you go ask him.
I'm pretty sure he does, because we use them for bioethics all the time.
If you go ask him, that'd be sweet.
Yeah.
Okay, so we're going to determine your guys' mass. We're going to measure the height of a stair. We're going to count the number of the stairs. And then you're going to calculate the height of all the stairs. And you guys are going to time each other as you run. If you would like, you could take a practice run and then give us the real run. Don't do too many practice runs because you're just going to wear yourself out. But if you want to warm yourself up and get, a handle on running up the stairs, what I do want you to do is I want you guys need. Do I care if you touch every stair?
Yeah, that's what I was wondering. Will it affect us? No. It'll make us slower. It'll just make us slower.
You can choose how you go up the stairs.
Fast as possible.
Okay? You can choose how you go up the stairs, because all we care about is the total height, and you're going to have to time each other. So if you want to take a practice run at it, you're welcome to take a practice run at it. We're just doing a new 1 flight of stairs, because you'll lose time with the corner.
Wait, our school is half flight.
Whatever. You're going up 1 straight stack of stairs. That's what you're doing. You do not want to turn the corner, because that's going to detract from the length of time. Because you're not going up during that time. You only want the time you're actually going up.
Cut the time there.
No. That just adds more error. You're not that good. Okay, so I have rulers. Every group grab a ruler. You're going to want to be careful with these rulers because they don't start at 0. There's a bit of a gap. So what I would recommend you do is do not measure. Okay, Naya and Jasmine, one sec. Do not measure the distance from the floor to the height of the first stair. Measure the first stair to the, line that up with 0 to the height of the second stair, and then multiply by how many stairs there are. Okay? You guys are going to have to split yourselves up. I don't want multiple groups on sections of stairs. So we've got space for 1, 2, we've got 3 in this stairwell. Groups of 2 or 3, that's it.
I'll zoom up these stairs, bro.
Grab a ruler, let's go.
Hey, bro.
We'll do all the timing first, and we'll figure out the masses later.
Absolutely. Nah, I don't actually do that. Super calculator. Mine fully. You're accustomed to that. What? You're accustomed to this.
the biology department and the physics department, we had
We have like a good one.
a scale, but yes, a good scale.
But yeah, no, Mr. Mr. Cook was on the phone complaining about something being charged to his credit card, so.
As you do,
Yeah, exactly.
you're teaching the class.
No, he, right now would have been my biology
okay.
class.
You guys are done? You got your times?
Yeah.
Let's see what we got.
I did it in, 3.94.
Okay, and you got the height of all 16 stairs, or how many stairs there were?
Yeah, we measured the first one, so
Okay.
then we're just gonna do
So yes, your scales right here. Do be aware, so you want kilograms, not pounds, so it's these small numbers. The inside one, and it's out by half a kilogram.
Oh, okay.
Not mistaken. Yes. So yeah, way up.
Okay.